Hi everyone. In today's in-person question and discussion session, we were trying to cover how we can code Perceptron. Unfortunately, we ran out of time, so now I'm recording everything, all the entire process, and I'll try to walk you through how you can compile your own Perceptron. In order to start with this, as usual, I will start a terminal. It's right here. Let's move this to the left, and then we say vim Perceptron py. As I kept on saying this in the previous cases as well, you don't have to use the terminal. You can use anything you want. We are not restricting you to any specific editor or anything like that. So now we have this thing vim Perceptron, and we will just do the basic shenanigans of Python. Basically import numpy as np is one thing, import says is another thing, of course, and we do if name equal to main underscore cs dot exit main right here. Okay, let me also set the numbers so that we can see the line numbers too. And of course we need a function called main, and it is right there too. So that being said, I think the next thing we want to do is to make sure that this main function runs as intended, and we can just print hello for now. Okay, so let me start another terminal right at the bottom, and I say python 3 perceptron.py. If all goes well, I see hello, and it's what I see. Maybe we can just make this slightly smaller because we don't need this to be big and consuming space on our screen. So next thing we want to do is to understand what we need to code in the first place. And a good way to do that, if I find lecture notes for the 4th week and put it right here, and maybe I can dock this to the right hand side and move you towards slide 14. Slide 14, this one over here. If we think about this specific one, this specific Perceptron related slide, we want to code that one. So in the start, obviously we need some data with labels. This will be our training data. Some of you ask me, what is a test data? What is a training data? Training data is the data you used for training a model. So you use it in the training time. Test data is the data to test the trained model. So these are two isolated data sets, okay? We need the training data to find the parameters of our model, our Perceptron, to be compiled. So that being said, the next step we will be needing is, of course, obviously, after having this thing, is to feed the training data to the Perceptron training mechanism, okay? And obviously, you want to visualize the outcome. For visualization, oftentimes we rely on matplotlib, but matplotlib is not the only library you can rely on. There are so many other libraries out there. I'm just going to keep it simple, and I will say matplotlib.py plot splp. Okay. So entire structure I have described here, entire thing I've described here in line 7, 8, 9 requires me to code 3 different functions. And let's go with this first function. Let's first build this Perceptron. Maybe this is the first step. Let's say feed the training data to a Perceptron training mechanism. Of course, we should have some assumptions about the data too. If you recall, maybe if we can go back to week 3's slides. Let me do this real quick. and put this one over here. And if I go to slide number 30, remember I told you guys that these circles with colors on it, like blue and orange, they are our training data. These are our training data, okay guys? And the space, these little dots where we try to classify the space, these can be like the test data if you like. And in the specific case, you remember what's going on, so I won't repeat it. But assume we have such data like this x and y values. This one circle has an x and a y value. So if I code this Perceptron function, obviously I will be needing such data in my definition. Let's change this. Okay, this is better. And we will say we need, let's go back to slide 4. We need this x, bunch of values in x and y. Okay, x. This is a NumPy array. Input x, y pairs. So since it's x, y pairs, there are m points, and it has 2 dimensions. One of them is representing x, one of them is representing y. Okay guys, so if I go up here, we find the first input to our Perceptron, it's x. So let's read this really carefully. The Perceptron is just a bog standard linear classifier. That's true. And linear decision boundary at this, okay, x dot product w is equal to 0. It uses an undifferentiable 0-1 loss. Undifferentiable means you cannot take the gradient, so you cannot differentiate. So there is a standard rule to update this model in this classification model. So the Perceptron algorithm is a method for iterative training, such a model one training sample at a time. Okay, this is also a good insight. It says one sample at a time, so probably there will be some sort of for loop in that case, and in that for loop we will be finding the data ID in range x shape 0, right? Because if I have m points, x shape is m, right? Let's say if I have 100 points, I need to go through from 0 to 100 and pick the data and then run it through the Perceptron. Why do I need to do that? Because it's written in the slide 14, as you can see. It's also in the description. Effectively performs stochastic gradient descent. Remember guys, what was the stochastic gradient descent? Stochastic gradient descent trains on patches, whereas the gradient descent trains on your entire data. Let's move forward and try to understand this a little bit better. Slide 15 gives us a little bit more idea. It says there's some value called w, and it's initialized as 0. W is the weights, is what we are trying to find out in a model. Okay, so we can say weights is equal to np zeros, and then I can say x shape 0 1. I can also say that, right? And I have just initialized w as zeros. It's filled with zeros, but it should have been 1 here, because let me give you the brief description. As I told you guys in the class too, at the end of the day I'm trying to fit something like y is equal to x0 times w0 plus x1 times w1 plus x2 times W2. So this x0 can be one dimension of this x, the x values. x1 can be the y dimension. Remember, a dot is x and y, right? So here it's represented with x0 and x1. But in addition, I added a bias term here. It's not always needed, but it helps to converge to a better solution. In some cases it's not needed basically, but I will say x2 is always 1. It's always 1. So in order to have such weights W0, W1 and W2, if I keep it as x shape 1, 1, like in here, it will be 2, 1. But I want this to be 3, 1. Why I want this to be 3, 1? Because look at here, line 12, I said I'm trying to train this in this model, right? So basic way to achieve this is to add 1 here, right? Now you know the reason. Okay, let's save this. We had the x value. Okay. We also know that we initialized it in the right way. We also know that a perceptron runs across number of iterations. So we need something like iteration number 100, let's say, initially, and then I can have another for loop for step in range iteration number. I have two loops, they are nested, and you can see that this goes from 0 to 100 and this goes from 0 to whatever points, number of points you have. Okay, so far I think we have compiled some bits, and let's try to see what's next. So in slide 15, do you see this predict y hat 1 x dot product w bigger or equal to 0? Let's also try to write that. But before we do that, let's understand. And this is our model, right? This thing is our model, and y is our prediction. Basically, we have classes, right? When a number arises, it can either be blue or orange, like in this example, or 0 or 1, something like that, some other class or so. So y hat, the prediction will spit out 0 or 1 in this case. When does it give you 1? It's if x dot product w is larger than 0, it will give you a 1. If not, it will give you a 0. Let's also model that with another function called model. Def model, it takes in x and w, right? And then returns some value. Let's say return 0 for now. But let's also build this in the right way. What I'm going to do is, like, I need to have value is equal to np dot. I'm writing this dot product only at this time before I apply an if statement here. np dot xw. But if I write it like this, remember x is 1 point, and that point will be like x y value and then 1. Remember why it's 1? Because I was trying to add bias here in the weight. So it's 3 to 1 in dimension. This x is 3 to 1 in dimension. Our weights are also 3 to 1 in dimension. In order this dot product to give us a scalar value, we need to take the transpose of this thing in, so that the dimensions fit and we have the right calculation. So we have the value now. And since we have the value, we can do comparisons. We can say if value is bigger or equal to 0, return 1. If not, it will return 0. So we have the model, we have the prediction here. So we can go back to our perceptron and say y hat is equal to model xi and then weights. And let's also define what is xi. Xi is one point we choose from our data set, and that is x data ID. Of course, we also need its label for future use. yi is equal to y data ID. Okay. So, but remember, this is 3 to 1, but this is only x and y. So we need to insert the bias component too. We can do that by using this handy function called np-insert. np-insert. And then we can say comma 0, 1, and then to make sure everything looks in the right shape, we can say reshape -1. -1 here refers to whatever remains, and then 1. We dictate the second one to be 1, and then -1 means here whatever remains. And it's, if you're lucky, this should return 3 to 1. Okay, guys? 3 to 1. So we have the data, we have the label, we have some prediction mechanism. In the rest of this slide, it says update, and there's some update rule. But it also says only update weights when prediction is wrong. But how do I know the prediction is wrong? A good way to know if a prediction is wrong or right is to compare it against the ground truth data, is to the original label. And we can do this with another if statement. If y hat minus yi is not 0, meaning if there are two different values, okay, then update my weights. So it says the new weights is equal to weights plus weights is equal to weights plus, and then we see this alpha here. Alpha is a hyperparameter. It is also known as learning rate. Learning rate. Say 0.1. Just make this up, and then if I say like something like learning rate is equal to float, and I say learning rate as a description, and I can also add documentation related to iteration number to do this in the right way. And then I say iteration number is an integer because we can have integer numbers in our range, and then we can say iteration number. So these are our parameters. And of course our returns will be the trained weights. It's a numpy array again. Trained weights of our model. In this case it will return 3 by 1. Okay. And a function to train a perceptron model. Okay, we have the right documentation at the top. Now we can go back to this update rule again, because we have the learning rate defined. We can continue writing this slide 15's update rule here. We can say something along the lines of learning rate times. We have a parenthesis here. It says y. Y means the original label. We know the original label because we feed it in our data. It's y_i minus y hat. This is our prediction, y hat. Okay, and then it says also multiply this with x data. Remember, we load the data one by one, so it's x underscore I. So we have an update rule to update these weights. If we are lucky, when all of this thing is done, we will be left with some meaningful weights. Okay, the first bit I think is complete. The feed the training data to a Perceptron training mechanism that we have done already. We can just say like weights is equal to Perceptron, and then we need to also feed the labels, right? So there should be some sort of y here, and it's y here, and it's again numpy array, and it's labels for the input data, and it's m times 1, because this xy pair can be either a member of 0 class or 1 class. Like it's like you can think of this 0 and 1 like a blue class or an orange class. Okay, now we have this, we have the model, we have this entire thing assembled here, so we can just feed the data x training data, which will create y train data, and then we feed in some learning rate, whatever we want to feed, learning rate, and then we have this iteration number equal to iteration number, which we will also define. This line is too long, so I will just break it like this to make it look more tidy. Okay, we have this one to learning rate, iteration number, and everything. Okay. Before we move on to visualization, of course, we need some data. Let's also think about this some data bit. Let's clear this part, and let's say we need a mechanism that will provide us x train and y train. Okay. And I would like to do something like this. Maybe before we define x train, y train, let's keep it here. Let's not delete it. We need to define two set of data for two set of classes. Let's say we will first try to figure out xy, y, x0, y0, and let's say we also want to define x1, y1, the labels for these things. I think if we have something like generate data, let me also, before I forget, learning rate here is whatever we want it to be, 0.1, iteration number here is 100. I will now compile something called generate data. Let's go into this thing too. Generate data. Of course, it will require number of elements I want to generate. Of course, this will require this, and we can also add this as our documentation here. These are parameters. We can say a function to generate reasonable data with a specific class. Okay, parameter, and then I say number of elements, it's integer, number of items in elements, and the final data, right? And then we said we will define a class. We can say label is something. It can either be the class of 0 or 1. Okay, label, this could be a floating number, that's fine. And then we can say choose your class either 0 or 1. Okay, that's also there. What this will return at the end of the day, it will return some values for me, right? It will return x values. These are numpy arrays, values that represent the generated data. If we call this number of elements as m, then this is going to be m times 2. And then we need y, which is numpy array again. We can say labels for the generated data, and we can say m times 1. Now that we have a plan about how to build this thing, right? So we can say return x, y, and the rest is to code this thing in the right way, right? Number of elements. So in order for me to generate random values between 0 and 1, I think I can rely on points x and p random dot rand, and then I can say number of elements to be, I will just generate like whatever this, let's say if it's 100, I will generate 100 by 1 values between 0 and 1. But remember, if I want to do this in an effective way, it's best for me to work with separable functions, right? Separable data. You may recall what separable means. I think it's shown here, maybe in the very beginning of this third section. Is it? No, not this one. How about this one? Is it in fourth section? Maybe second one. Just give me a second. I want to show you what I mean by separable. Is it here? Is it here? Yes, that's a good example. This is a good example. It's separable data. It looks like this, so that I can. Is there also a boundary shown here? Maybe not. But anyways, if we look into this data, I want to create something similar to this so that I can play with, and I can clearly say like this is the boundary. This whatever the data here are blues, whatever the data here are oranges, or zeros and ones. So okay. Yeah, so we can generate such data basically accordingly. Okay, we were generating this x data and we need a y data, right? Points y, and that's also rand number of elements 1. But if I use 100 to 1 with this rand, it's going to be between 0 and 1. Whatever I generate will be stuck here, 0 and 1 here, and then 0 and 1, whatever, like it will be somewhere here. It's not shown in this figure. The values of x and y will be stuck between 0 and y. But I don't want that. I want them to accumulate around some center. And I can define that center with a shift. I can say shift, we add something like a shift like this one, and then I can add another shift here and a shift here, and I can say, or maybe instead of a shift, maybe let's call it center. It's better, center, or offset is actually offset. Okay, so if I keep this value, to be 0, 0, these values will be between 0 and 1. But if I keep this value as, let's say, 5, what's going to happen is like these values will be between 5 and 6, right? So I shifted in space using this offset values, and I can just add this in my documentation by typing offset, which is a Python list, and I can say offset along x and y axes in the generated data. You may also want to scale it, right? You may also want to scale it. If you want this to be not between 0 and 1, you can just, you know, multiply it with scale 0 and then scale 1, right? And then maybe we can add this to here too. Maybe we can add this to here too. Scale is equal to 1, 1. If we keep it as 1, 1, then of course it will be between 0 and 1, but if we keep it as 2, for example, it will be 0 to 2 in this case, the random values, because I'm scaling it, as you can see, by multiplying it. Once I have that, this is some numpy rate between 100 to 1. And this is also between 100 to 1 if I choose this number of elements to be 100 to 1, right? But I don't want that. I want 100 to 2. I want these to be stacked. I want these to be concatenated so that I along the different, you know, axes, so that I can you know, use this later on as one giant X, right? As one giant X. Okay, so one thing we are missing, we should also add some documentation related to scale. We can say scale is a list and scaling factor for data for points generated along x and y axis. Okay, we have the right documentation here now. Now let's generate this x. We need to merge those 2 points, x and y, into a 100 by 2 numpy array. And numpy is this handy tool called np-vstack, which will help us points x and points y to be stacked along the second axis, the vertical axis. And for sure we will be needing labels, right? Labels are the it's basically np1's number of elements by 1 times the label. If my label is 0, I will get labels in the size of 100 to 1, 100 to 1, and it will be all filled with 0. If my label is 1, I will get something 100 to 1, it will be all filled with 1, and so on. Maybe we should call this as y, but you know what, maybe it's better if we call this point in the first place, points, or maybe data is a more descriptive, data and labels. Okay, maybe that's more descriptive. Data, let's change this. Labels. Okay, we have a mechanism to generate data too. So let's also use this here. Generated data is, we have, let's say I want to have 100 different points, 100 here, and offset is, I don't know, I'm just maybe like 4.4, and then I can say, for now let's keep the scale as 1 so that I know those the second values that I'm going to assign, they will also be separated enough. Label is equal to 0 in this case. And oh, what did I do? Okay, yeah. So if I do generate data here, again 100 data offset, let's put this along this other axis. It's 4, and then if I do this like -4, and then I use the same scale to be 1.1, and then label is 1. Let me just stop things right here with a says exit so that it won't be, you know, moving forward after this. I want to print the shapes of this data. Print x0 shape and y0 shape, just to see what this spits out. Okay, so it's 201, 101. I think we are doing the wrong thing by having this v stack. Probably what we want is h stack, because when we stack them together, it doesn't end up being 100 to 2. It ends up being 200 to 1, right? Let's try it one more time. Okay, now I have the right shapes, 100 to 2, 100 to 1. I have the data, right? Remember I created two classes. Let's try to think of what just happened. x0, y0, these are around 4 by 4 and their label is 0. And then we have this labeled 1, and this is between closer to -4 to -4. So we want to combine those two class data and make a mega data, let's say, that is containing all these data that we need for training. And we can do that again, one more stacking, right? We can say np, maybe I can say x train is equal to np h stack, and then I use x0, x1. Let me first test what's going to come out of this thing by another print x train. Oh, I shouldn't print x train. I want to see the shape of it. Remember, this is 100 to 2. This is 100 to 2. What I want to achieve from this stacking is 200 to 2. Okay, let's see if this is the case. It's doing 100 to 4, which suggests me I shouldn't be using h stack. I should have been using v stack instead. Now I have this 200 to 2. Let me also do this for the labels for my training data, which is mpv stack again, and then I do something along the lines of y0, y1, and then let me also check its shape as well. Train.shape. Okay, I have the data, I have the labels. The data is x and y values. So to write this slightly in a shorter form, I can do some things like that. I can also do this, right? Oh, sorry. I can probably also do this, comma here, and then iteration number. Okay. Now I have this thing. I provide this x train, y train, and then we get some weights. Hopefully, let's try this. Print weights. Bear in mind, nothing works at the first time, so we will try to see if something goes wrong. Oh, it works. It just works. How come? Okay, let's see. That's interesting. We should also say things like taken from slide 14 of COMP0088 module. Okay, taken from slide 14, 15. Okay, so it looks like it's doing some training, but we want to understand if this is right. And in order to understand it, I think we need to first visualize our points, and then we try to see if we are doing the right thing or not. Okay, so I can just delete this line and delete this comment where we arrive at this final stage, plotting, right? I can say we need plot data function, which takes in our x train, y train, and weights, so that it can show us our training data and the boundary between those two, right? And the boundary between those two. Okay, let's write the same thing here. Plot data x, y, weights, which is w. Okay. I can say something along the lines of function to plot data and a boundary drawn using the given weights. Okay. Okay, so if I say something like I guess I need to first create a figure, plot figure. Okay, and then I need to show this figure at the end of the day with plot show, right? And I need to plot points from X, right? And then label them with the right color using Y. And in order to do that, I can use scatter. I think you can use scatter to draw things like this. Plot scatter, and I know that the first dimension, which is the 0th dimension, is X values, and the second dimension is the Y values. Let me first try this before coloring. I just want to see if this is working at all. Okay, let's see. Okay, we have these data, one here, one here. Let's see if we can also draw a line using the weights in between those two. But before doing that, I think I also need to change the color of this. If I remember correctly, it's either color or C. Let's start with C. C is equal to, because Y is the label, I can maybe use it directly with like this as the color. Does it work like that? Let's see. Oh yeah, it works. I think you can see that this is now colored like this, and this is colored like this, right? Next thing I want to understand is to figure out if we can draw the boundary line using the model parameters. And all I need to do in this case is to have x1 is equal to, I need some x1. This is going to tell me the bounds of this line that I'm going to draw, and I can say I need a minimum and a maximum value. I need this minimum and a maximum along x-axis, right? Along x-axis, so that I can identify the y values with using some. The reason I don't directly call this x, because we are using x, that's why I'm using it x1. So I need to look into the x values first and find out what is the minimum and the maximum, and I can do this by using the x original data provided here, and I can also do the same thing here to find the minimum and maximum. Let's see, print x1 here. Does it help? No. Okay, maximum goes here. Oh, I need to have the brackets. Okay, now it should work. Okay, we have the maximum and minimum, minus 3 point something plus 5, which makes sense as we know how the random works, right? Now I need to find the y values, right? And in order to find the y values, draw a line using the weights. I need some sort of m and c. What if you can recall, it's a line is basically drawn by y is equal to mx plus n, right? Or mx plus c. So x1 is my x in this case, and I need to find m and n. Let's call it like this. And m can be calculated using the weights. You can say I have weights here, w, and I want to take the first parameter from that and divide it into second parameter. This is my m, and I can do the same thing to find n, which is minus 1, 0th parameter in this case, and then I divide it into w2, the third parameter. Okay, this is cool. Now I have x and y's. Can I just plot this as a line? PLT plots. I think this is the moment of truth. Let's see if this is going to create the boundary with the trained weights. Yep, there you go. There you go. This is the boundary. This is the boundary that tells me how to classify the classes. If it's above this, it's this type of class. It's there, it's this type of class. Probably it's 0 and 1. Okay, what else I can do here? Let's give it a try a little bit more. If I extend this intentionally, like, does it break? If I just, make this 2. Okay, it's okay. Maybe if I do this like, I don't know, 5. Quite, yeah. If I extend this also here in 5. Maybe I can do this here too, 4. I'm just trying things. Let's see. Yeah, still I find a good boundary, as you can see. Okay, this is a perceptron. We give the learning rate, iteration numbers, and it spits out these weights, and we can, using these weights, I can just find the boundary between 2 data sets classified with different classes. Of course, this is a very simple experiment in this case. It's very obvious that those 2 can be distinguished by looking in the XY space, but in some cases, there might be much more intersections, and you try to find some boundary that does a fairly better job than just randomly choosing basically which class to choose for your data. Okay, I hope this was useful for you guys. Please do let me know if you have any questions related to that, and I will also post this entire code on your on our Moodle, so you'll be able to have an access and get a copy of this thing as well. And I hope you find it useful. Okay, thank you for listening. Talk to you in the next iteration.